We're recording, so be careful what you say. Today's Friday the 13th. And we're just going to look at electrophilic substitution of benzene. Again, we'll have a little bit of a reminder of that because we already started this in the last lesson. Just a reminder, what's an electrophile? Say again? Electron pair, please. Electron pair acceptor, yeah. Electron pair acceptor. And by substitution, we mean yeah, swapping one group with another one. Usually a functional group is quite hard to swap a non-functional group because it doesn't have anything we can get to it with. Okay, so we'll start off with nitration. So we did this at the end of the last lesson, but let's just review it anyway. How do we make the nitro electrophile? What do we need for that? You remember?
Nitric acid and sulfuric acid.
And they both have to be
Concentrated.
concentrated. So nitric acid and sulfuric acid combine together, both concentrated acids. It's a very vigorous reaction. It gets very hot. We need to do it on an ice bath to make sure we keep it cool. And sulfuric acid acts like an acid. HNO3 acts like a base and gets protonated by the sulfuric acid. So that's an acid-base reaction. It just looks a bit strange. The H2NO3 then breaks down into our electrophile NO2 plus and water, which presumably gets mopped up by the sulfuric acid. Okay, that gives us our electrophile. First step of the mechanism. That's a good sound. See if that one turns up on tape. The electrons from the ring, those delocalized, the P cloud of electrons, which are able to move around, can come out and attack our nitro group. And we make this smiley face intermediate because we've broken the ring. Remember that our carbon that's being substituted, it starts off with a hydrogen on. We don't draw them, but all benzene carbons have a hydrogen on. And it's important we're really precise about the way we draw our intermediate. So the arc that goes around should go from one adjacent carbon to the other adjacent carbon and completely miss out the bonds there between the adjacent carbons and the one that's being substituted. And the plus charge is held by the ring. It should not be anywhere near that carbon. That carbon it's got 4 bonds, which is what every carbon wants, right? So there's no need for any charges there. It's fine. But we've lost an electron from our ring, so that's got a positive charge. And then our final step is we take electrons away from the carbon-hydrogen bond here, return those to the ring, and we've made our ring again, but now we've got a substituted position with the NO2, the nitro group, so we've made nitrobenzene. And we've released H+, and the H+ can then combine with HSO4-, remaking the H2SO4, and because that's been reformed, it's catalytic. We're never going to run out of sulfuric acid. Okay, so just really focusing on the details there, because some of you, you're not draftsmen, let's put it that way, and sometimes your diagrams get a bit loose and a bit well, wrong. That's really the word, isn't it? The arrows in a mechanism have to be very precise. The charges, the arc, everything has to be in the right place. Any questions on any of that? Okay, so that's, as you can see on the board, that's number 1. The other type of electrophilic substitution that we didn't get onto last time, but it's going to have a similar process, is Friedel Crafts acylation. Is it Friedel or Friedel? I can't remember. Friedel Crafts were presumably 2 scientists. I don't know if I'm speaking about this on YouTube. I should really do my homework beforehand, but I can't remember where they came from. Anyway, they came up with the catalyst for the reaction. The catalyst is AlCl3, aluminium chloride. And if you just draw a little dot and cross diagram for me of aluminium chloride, please. You just draw that simple sort of GCSE style dot and cross diagram of aluminium chloride. Share out its electrons. Aluminium in the middle, 3 chlorides around the outside. A few more electrons on the chlorine, presumably. It's not the vital detail, is it? Then, having done a quick flick at the periodic table to check, you realise that aluminium's only got 3 electrons in its outer shell. Of course, the chlorines have 7, so they're fine. But that leaves chlorine with a vacancy in its outer shell. It's only got 6 electrons. It's not a complete outer shell. That allows, I haven't left myself enough space, have I? But that allows another chlorine to come along and fill that outer shell. So we could have a reaction where we can make AlCl4 minus using a chlorine. And we can use that reaction, but because aluminium chloride is really very keen on getting that chlorine, it really wants to fill its outer shell, we can use that reaction where aluminium chloride robs a chloride of something to force it to make an electrophile. And here's how it works. We use the AlCl3 on ethanoyl chloride. You might remember from carboxylic acids and all that jazz that's our acylating agent. What's the acyl group again? It's an odd name, but it's one that's stuck around. What's the acyl group? It's what? No, that's not the acyl group. No, that's not right. We used acylation with additional elimination reactions in making esters and amides.
CH3CO.
Yeah, that's right. CH3CO. That's that bit of the group taking off the chlorine. Yeah. So if my aluminium chloride robs the chloride off this molecule, you should be able to see that we'll make AlCl4 minus and then CH3CO plus. The plus charge, should I just draw that out a little bit more clearly? Because the plus charge is down the carbon end down there. Okay, again, as for nitration, you need to know this reaction. That's part of the mechanism, knowing this reaction, knowing how we make the electrophile. But the next bit should be fairly familiar. If I present, I'm just going to switch it around. So we've got the plus charge facing the benzene ring. If I present my benzene ring with an electrophile, now we're on the home straight. Everything looks fairly familiar. The electrons from the pi cloud come out and attach themselves to that carbon. Remember, the direction of the arrow shows us the direction of the lone pair of electrons. I'm going to go with this carbon for a change. Okay, the same thing, but kind of on its side. Again, the arc goes from one carbon to the other carbon, missing out the middle one, and the plus charge is safely in the middle of the arc there. But instead of adding the nitro group, we've added this COCH3 group. Okay, and then those electrons from the carbon-hydrogen bond get taken back into the ring, and hooray! We've got our ring back, and we've now added the acyl group onto there. What's the last bit? What was the last bit last time?
Regeneration. The catalyst.
Regenerating the catalyst. So obviously this reaction releases an H+. There it is. That H has been released as an H+. This time we need that H+ to react with our AlCl4-. Do you remember that was the product in the electrophile forming stage? So we've now got AlCl3 back again, and we'll make a bit of spare HCl. Regenerate